Okay, here we are at Module 3B. We're going to look at the entropy change of ideal gases, and we're going to look at ideal gas tables, and compressibility, what we do when it's not an ideal gas. And finally, we'll review all the properties we've done so far. Let's talk first about the entropy change of an ideal gas. We have, for an ideal gas, ds equals Cv dt over T plus R over the molecular weight times dV over V. So we've written it as a function of two other properties, in this case dt and dV. And if you know Cv, you can calculate this for an ideal gas, Cv and the molecular weight, of course. Another representation which you can show one equation from the other using PV equals nRT. You can prove the second equation follows from the first. ds equals Cp dt over T minus R over molecular weight dP over P. Now, for constants Cv and Cp, we can integrate this and get delta S. Remember, delta S is S2 minus S1. Delta S. And then we can say delta S equals the integral of dt over T, of course, is ln of T. Evaluate that between the limits, and you get Cv ln of T2 over T1 plus R over molecular weight ln of V2 over V1. Similarly, we have an equation for delta S depending on the T's and the P's. So if you know T's and P's, you use equation 2. If you know T's and V's, use equation 1. We'll use this a lot when we get into problems involving entropy. Now, I want to talk about ideal gas tables. Now, this is going to apply to particularly to those of you in mechanical engineering, and for those of you in chemical engineering, we have other ways of dealing with it that basically come to the same thing, but we usually don't list it in tables. Ideal gas tables are usually used for common substances such as air, nitrogen, oxygen, and you'll find those tables in your book. For chemical engineers, we have all kind of different compounds that we're looking at, or materials that we're looking at, and so we have a more general way of doing it. We'll usually use the Cp dt over T minus RdP over P, say for delta S, or we'll use du equals Cv dt for an ideal gas. And we'll use that for all the different substances, and we don't really have tables. We could make our own tables. For those of you in civil and electrical, you won't see this as much or need it too much, but go ahead and follow along. This is what I call lagniappe, and particularly for mechanical engineers, you guys are going to need this for your next course. Listed in your tables are temperature, enthalpy, internal energy, and what we call the entropy with a little zero in front of it. The bar indicates that often these are listed in molar units, so depending on your text, you'll find it in molar units. Sometimes it's in mass units, but molar units would be giving you enthalpy in kilojoules per kilomole rather than kilojoules per kilogram. It's easy to go back and forth between the two by just multiplying by the molecular weight. Now, for a reference state of 0 degrees Kelvin, remember we talked about the reference state, and any tabulated value of energy is relative to some arbitrary place that we call 0. So if we take the reference state to be 0 degrees Kelvin, then U bar is the integral from 0 up to T of Cv dt, because remember, for an ideal gas, du equals Cv dt. So we just integrate it all the way up from 0, and we get this value of U that you'll find presented in your tables. For H, we'll have the integral of Cp dt. And for S0, that's only the temperature part of S, integrating from T0 to T of Cp over T dt. You recall delta S was Cp, or ds was Cp dt over T minus R dP over P. So your tables leave that part out and allow you to calculate it later, and so we'll save that for another day. Now, the next thing we talk about, and again, this is Lagniappe. Mechanical engineers may have to deal with this if you get to high pressure processes. Chemical engineers, in your next course, we're going to get into this in great detail. So for now, just treat it as Lagniappe, read through it, study the material, get familiar with it. I want you to hear it once, but you're going to see it a lot more. Whenever we have a high pressure process, we have to deal with the fact that the gas is non-ideal. So we'll represent it often. This is one model for representing the non-ideal behavior of a gas. We'll say PV equals nRT, but times this Z, which is correction factor. The correction factor is called the compressibility factor, Z. And Z is a function of the temperature and pressure, and I say scaled to the substance. Now, a little while ago, I told you that compared to the critical point of a substance, most substances behave similarly, and that's the compressibility theory, or the generalized theory that all gases sort of behave the same when they're compared to their critical point. So if we scale that temperature and pressure to the substance, we can calculate this compressibility factor, which corrects the PV equals nRT behavior to a real gas. And that's how we compensate and calculate the PVT behavior for a real gas. Okay, we do this by defining a reduced temperature, which is T divided by the critical temperature, and a reduced pressure, which is P divided by the critical pressure. General in that gases behave the same relative to their critical temperature and pressure. Again, this is saying that many gases, or all gases, most gases I should say, behave the same relative to their critical temperature and pressure. It does get more complicated, and in your next course in chemical engineering, say, we'll look at several different models that even get more complex to deal with the non-ideal gas behavior. Now Z is the departure from ideal gas. Now we look at the T versus V behavior of T versus V behavior of water or nitrogen. You see, of course, that this critical point is much higher for water than it is for nitrogen. Nitrogen, therefore, is more likely to be an ideal gas at room temperature than water, because remember, ideal gases occur at high temperatures and low pressures, and the temperature relative to its critical point, so room temperature, is very high temperature for nitrogen compared to its critical temperature, but not so much for water. So now let's take an example. If we take nitrogen at 300 K and 50 bar, that's 50 atmospheres. It's really high pressure. Then the reduced temperature we calculate, 2.38. And the reduced pressure for nitrogen we calculate as 1.47. Now, of course, this is 300 is our temperature, 50 is our pressure. The critical temperature for nitrogen, 126 Kelvin. Okay, that's really cold. The reduced pressure for, the critical pressure for nitrogen is 33 bars. So that's, that's pretty high pressure. But really, we're looking at the temperature as being very, very cold, the reduced temperature for nitrogen. So 300 is more than twice that. We've got a reduced temperature of 2.38, so we're very high temperature relative to the critical temperature. We calculate Z, and Z you'll find in charts in your text. You enter the chart with the reduced temperature and the reduced pressure. You'll find Z is 0.98. Okay, remember, Z is the correction factor, so it's like 98% of being an ideal gas. Think of it that way. It's very, very close to ideal gas behavior. Okay. Okay, now let's look at water at 300 K and 50 bar. Oops. Let's look at water at 600 K and 50 bar. Now that's twice the temperature that we were looking at for nitrogen, so we'd expect it to be even closer to being an ideal gas. Remember, ideal gases occur at high temperatures and low pressures, so we'll look at even double the temperature of that we had for nitrogen. We would expect it to be close to an ideal gas, but as we find, the reduced temperature is only 0.927 because you've got this very high critical temperature for water. So the reduced pressure, 0.226 for water, and we find that when we calculate Z, it's 0.90, which is only 90% of being an ideal gas compared to nitrogen, even at half the temperature, was 98%. So again, this reduced temperature and reduced pressure can get you into the Z table or the Z chart that you'll find in your text, and you can find that ideal gases, or how close you are to being an ideal gas, depends on the particular substance that you have. Okay, there's a couple corrections that we need to make to this compressibility factor, and those are for hydrogen, helium, and neon. We have to correct the TR and PR with these equations here. So just remember, if you're dealing with hydrogen, helium, or neon, then you have to make a little special correction to this reduced temperature and this reduced pressure to enter the chart. Okay. If you know V and T or V and P, then you can use what's called the pseudo-reduced volume to enter the chart and find VR is equal to this VPC over RTC, and then you can back calculate, for instance, the pressure or the temperature if that's what you're trying to find given the volume. Typically you'll want to know volume given temperature and pressure, but you may need to know temperature given volume and pressure, or pressure giving volume and temperature, and this is how you would do it. Okay, let's review everything we've done so far from modules 1 through, or let's say especially modules 2 and modules 3. Any two independent properties define the state of a pure substance. So for instance, we can find the internal energy from the temperature and volume, find the enthalpy from the temperature and pressure. Fine, you give me two properties, I'll find the third. Accordingly, properties may be presented as two-dimensional tables and figures. The Moliere chart is one that's of great interest. I have a little video on the Moliere chart, and that's a very handy chart to use. It presents in two dimensions the properties of a pure substance, and it plots enthalpy versus entropy, and very handy little chart to use for particular situations that we'll get to later when we start looking at processes. The superheated tables, that's presented on a page in two dimensions. You've got, say, temperature down the side and enthalpy across the to the right. Properties are generally described by equations which are used to generate those tables and charts. Now it's awfully handy to use tables and charts, but if you get into very many different types of chemicals, then that'll be reduced to some equations, parameters in equations that'll be used to generate those tables. These equations you determine by taking measurements of the raw data. Like for instance, you'll measure temperature, pressure, volume, and as those of you in chemical engineering will see later on, you'll have to use some math to relate enthalpies and heat capacities and temperature, pressure, volume. All that'll factor in to developing those tables and equations that show the properties. The ones we've looked at so far are for the ideal gas, and those are fairly straightforward. CP, CV is going to give you a lot of information about the energy of a substance, and PV equals nRT is going to give you information about the volume, temperature, pressure behavior of the substance. Okay, the equations of state may have a theoretical basis like PV equals nRT. That's what we call a theoretical equation, and it's based on molecular behavior. Or you can take something like CP, which you calculate purely from empirical data, meaning you collect a lot of data on CPs and you regress it using statistical techniques to find these parameters A, B, C, D, and E. And we just, basically, that's a data fitting equation. In some cases, one variable, now we talked about ideal gases, and in some cases, one variable may be enough to describe a property. And that's true for the energy of an ideal gas. Remember, we said that U is a function of T only, so that du equals CV dt. dH equals Cp dt for an ideal gas. Now for liquids, we had properties are a function of, recall, mainly T and a little bit of P. So knowing the temperature, you can go into the saturated tables, pull up the property of a saturated liquid, and that's going to be very close to the property of the liquid even at a higher pressure. The exception to this is for high pressures, we still need to calculate H's or delta H's by including the V delta P term in them, which is not very hard to actually calculate. Need to correct for H because remember H is U plus PV, and that P is right there in the calculation. For saturated mixtures, recall, we had to know if temperature and pressure are known for the saturated mixture, and we know it's saturated. That really isn't, those really aren't independent properties. Those really, if you know the temperature of a saturated substance, then you know the pressure also. So those two aren't independent. We need to have an independent property, and the one we used most frequently to describe the second variable for the state is the quality. And remember, the quality is the mass fraction, or the mass of vapor, divided by the mass of vapor plus the mass of liquid. Finally, you should be able to use any two properties to find the others. You can use charts, like the Moliere chart or a TS diagram. You can use tables, like the steam tables or the air tables. And you can use equations, and the ones we've used so far are the ideal gas equations. And to do all this, you need the following skills. You need algebra. You've got to manipulate that ideal gas equation often. You may need to manipulate the equation that has quality in it, or do some interpolation. You need to be able to do integration, simple integration. You need to be able to do interpolation, and there's single interpolation, double interpolation. I'm not going to hit you with that in this upcoming test, but you do need to be able to do single interpolation. And finally, ideal gas tables. This is Launa, primarily presented for you mechanical engineers. So go through and read that section in the book. You're going to use this a lot because mechanical engineers are often dealing with air. They're dealing with oxygen situations, but a lot of times you're doing processes that involve air, and those tables are awful handy to get the function of T in there. Remember, Cp is a function of T. If you don't want to integrate it, it's already been done for you in those tables. Remember, when you're using those tables, sometimes they're listed as molar properties, so you get the enthalpy as a per mole basis. Okay, so finally we had compressibility, and this is where we looked at the non-ideal gas behavior. If we want to find the PVT relationship for non-ideal gases, compressibility is one of those PVT relations. And we use reduced properties to enter the chart. And remember, The theory is that all gases behave similarly when compared to their critical temperature and their critical pressure. And so if we calculate a reduced temperature and pressure, which divides out the critical temperature and the critical pressure, then we can get the property, or the Z factor, to see how far off, or to calculate how far off of ideal gas behavior we actually are. And that pretty much concludes our summary and our review of properties. Next, we'll get to the fun stuff, which is using these properties. Finding properties is a skill. Once you get past that, you can do all kind of great things with them. And that's more the fun of thermo, when we get to calculating, finding processes, how to use these properties to find, well, to generate things like engines and refrigerators and all that good stuff. Very good.